Okay, so today we're going to talk about telescoping sums. Specifically, we're going to be talking about the general concept of a telescoping sum. In class, in class and in doing our research for this project, we found that depending on what source you go to, some people say, okay, the telescoping sum is only the summation in which all of the terms except first and last cancel. And that's the general. That's generally what we looked at in our study in EECS 203. But I was far more interested, and I think that it would be far more beneficial to look at the more general idea of what a telescoping sum is. And a telescoping sum essentially is it's a summation, obviously, in which there's some pattern, some repetition of positive and negative terms that cancel each other out. And what you're left with is a finite set of terms, or a finite number, rather, of terms that even under the conditions of being an infinite summation from 1 to infinity, you still have a finite number of terms at the end. And so, based on this, obviously it's very applicable to a lot of different things. This module is really just going to focus on trying to get people to recognize the patterns that cue you off to the concept of a telescoping sum. Alright, so let's look at a concrete example so you can kind of visualize what I'm talking about here in terms of cancellation. If we look at this following sum, the sum of a sub I plus 1 minus a sub I, you recognize, right, that these two, a sub I plus 1 and a sub I, are sequential terms in a series. And because we're subtracting these sequential terms, we're going to get cancellation throughout. So let's look at how it cancels. We can note, right, that we have a b sub 1 or b plus 1 term that's positive and a b plus 1 term that's negative. A b plus 2 term that's positive and a b plus 2 term that's negative. A b plus 3 term that's positive and a b plus 3 term that's negative. And so on. And so if we go through and cancel out all these terms, including the fact that we can do the same all the way up until the last term, we're left with the more specific case, the one that we looked at in class that I mentioned earlier, where the only remaining terms are a sub n plus 1, which is positive, and a negative a sub b. B, in this case, not 0, because we're starting from an arbitrary point. Next, I think we should look at the following sum and recognize, right, that the only difference between this and this is that the terms are flipped. And one way of accomplishing this, right, is just multiplying by negative 1. So if we're looking at this, what we expect to see is if we multiply both sides of this equation by negative 1, we expect that this summation would be equal to a sub b minus a sub n plus 1. And if we go through and look at our terms, we have cancellation. This is a lot cleaner because they're next to each other. The n sub 2's cancel, the n sub 1, or n minus 2's and the n minus 1 terms cancel, and the n terms cancel. And just as we expected, we are left with a sub b minus a sub n plus 1. So, what we can do then is generalize this. and say to ourselves, okay, well, if we have terms that follow the following rules, a sub j and a sub k, right, where the difference between j and k, the absolute value of the difference is 1. In other words, these two terms are sequential. Then, in the case where typically we're looking at, right, where we have the term a sub I plus 1 minus a sub I, or j, in our notation here, right, j is greater than k, we have just what we found up here. And in the opposite case, right, all we did was multiply by negative 1. So we have a sub b minus a sub n plus 1. And then this is a trivial case, obviously. When j equals k, right, let's say this was a j here, obviously this whole thing would just be 0 inside, and you'd be summing up 0, and obviously that's 0. But what I think is important to note is that this technique can also be applied when j minus k is a constant. It doesn't only work in this case, and we'll see that in the next slide. Alright, so this is a little bit, I wouldn't say it's outside the scope of the course, but we really didn't cover examples where the terms didn't differ by 1. But in fact, it does work if the terms differ by any constant. For example, for the cases of illustrating, let's take c equals 2. And first, let's just go through and do it the way that we've done all the previous sums, and just cancel out the terms and see what our final solution is, and then we'll try to make sense of why this works. So again, right, we notice that there is no term that's going to cancel that, and there is no term that's going to cancel the b sub 1. The reason being, right, is that this subtraction part is going to start at b sub 2, and the positive parts are going to be starting at b. So there will be no negative term to cancel out a sub b or a sub b plus 1. But the rest of the terms will cancel, right? So we can see that this and this term will cancel each other out. This and this term will cancel each other out. And you should start to notice that the pattern, right, in the previous example, when they differed by 1, part of this term would cancel with part of the succeeding term, or the following term. Whereas in this case, the part of this term is going to cancel with something 2 down the row, as opposed to the one right next door. And so let's just go through and do all that cancellation and see what we end up with. So the b plus 2's cancel, the b plus 3's cancel, the b plus 4's cancel, the b plus 5's cancel, and so on. And now looking at the back half, the last couple terms of the sum, the n sub 3 terms, or n minus 3 terms cancel, the n minus 2 terms cancel, the n minus 1 terms cancel, and the n terms cancel. And what we're left with are the following 4 terms instead of 2. So we're left with, again, a sub b minus a sub n plus 1, just like we had in the previous slide. But now we have an additional 2 terms. And so why is that? Well, first, we should think about, or we should notice, rather, that we can write this as 2 separate sums. And if we look at the expansion of both of those sums, we recognize, right, that this first term has a b and a b plus 1 that the second term does not have. And this second term has an n sub 1 and an n sub 2 that the first term doesn't have. And so we can rearrange this and recognize that this portion in here, b sub 2 up to n, or a sub b plus 2 up to a sub n, and this b plus 2 up to a sub n term will cancel each other out because of the negative sign here. So they're all going to, these two portions will completely go away, and what we're left with is just what we derived the long way before. And so I think this is really a good way to understand why telescoping sums work, is essentially, right, even if these were separated by 1, we could still break it apart into a double sum. And because these terms differ, in other words, because this one starts at b and this one starts at b plus 2, this one goes up to n and this one goes up to n plus 2, the portions that overlap between the two sums, right, here and obviously here and here, are going to cancel each other out. And the things that you're going to be left over with, or the things that are going to be left over at the end, are just going to be the fringes, the terms on either side that don't overlap. And so that's why, in the case here, right, we had, in the first example, only these two terms. Why? Because only when they differed by 1, there was only one one term, right, that fringed out on either side if we put it out into this form. Whereas, let's erase this just to make sure I don't confuse anybody. Whereas in this case we have two terms that stick out on the fringe. Alright, so enough with abstract sequences. Let's look at a real concrete example. So using what we've learned, and since we now know kind of the guts of how these telescoping sums work, we recognize that we want to label, we want to take this this specific sum, albeit an incredibly trivial one, and make it into an arbitrary sum of some form in which we have two terms that are sequential, that and we're summing up the difference between those terms. So in this case, let's just let a sub I equal I. So this tells us, obviously, then, that a sub I plus 1 is just equal to I plus 1. Which tells us, as you might have read ahead, that our original sum can be written as the sum of a sub I plus 1 minus a sub I. And using what we know, using the equations, so to speak, that we derived in the first example, where the terms were sequential as opposed to being a sub I and a sub I plus 2, we expect then that our sum is equal to a sub n plus 1 minus a sub 1, which, using our definition of a sub I, is just equal to n plus 1 minus 1, which equals n. So let's go through and check the hard way, and then we'll go through and check the easy way. But I think it's important to really pound home how the guts of these equations work, and to start seeing the patterns. So obviously 2 and negative 2 cancel, 3 and negative 3 cancel, 4 and negative 4 cancel, and so on. N minus 2 and negative n minus 2 cancel, n minus 1 cancels with the negative n minus 1, and n cancels with negative n. And just as we expected, the only terms that we're left with are an n plus 1 and a minus 1. So obviously, again, n plus 1 minus 1 is equal to n. So what we expected, and obviously this is a much simpler way to answer the question, is correct. Now, I noted that this was a really trivial example, and I wasn't kidding. Because in reality, it's a lot easier just to realize that I plus 1 minus I is equal to 1. So the sum of I plus 1 minus I is just equal to the sum of 1. So this is really just 1 plus 1 plus 1n times, or n. But in either event, we know that we arrived at the right answer by using the process of a telescoping sum. Alright, so let's do a quick concept check here. For the following sum, right, from 1 to 19 of 1 over I plus 1 minus 1 over I, let's let our a of I term be 1 over I, the simpler of the two. And it works out pretty nicely, right, because that means that this term here is a of I plus 1. So I gave away the answer to the first one, so I'll just I'll just show it to you. And so obviously, right, we can write it in this form if we define AI to be this, or AI to be 1 over I. So what's the general form from 1 to n in this case rather than 1 to 19? Well, we recognize, right, that the term with the larger subscript, right, in other words, the next term, the term that's one farther along in the sequence, is positive. Or in our terminology, right, j is greater than k. So what we expect then is for our general solution to take the form of a of n plus 1 minus a of 1, or a sub 1, because we're not dealing with 0 and we're not dealing with b, again, we're dealing with 1. So using this, right, what is the sum from 1 to 19? Well, obviously, we can just plug 19 in for n. But for the last time, let's just go through and check it out. Make sure all the terms cancel, make sure we get exactly what we want. And so we can note that the 1/2, negative 1/2 will cancel, the 1/3, negative 1/3 will cancel, this 1/4 will cancel with a part of the next term. Similarly, this negative 1 over n minus 2 will cancel with part of the previous term. The n minus 1's cancel, the n's cancel, and we're left with exactly what we thought. And by plugging in 19, then obviously we're going to have 1 over 20 minus 1, which is 0.95. Alright, so let's quickly look at some common pitfalls that people run into. What's wrong with this telescoping sum? Well, it's pretty self-evident, right, because it isn't one. It's an addition. We have addition between our sequential terms as opposed to subtraction. And depending on what sequence you're looking at, right, there may be some kind of cancellation, but it's not going to be the same kind of systematic cancellation that we can use to our advantage as in the as we have in the previous examples of telescoping sums. The second part, I think, is a little bit more interesting, right? And it deals with convergence and divergence. One, obviously, if we can use a telescoping sum to simplify this sigma, this whole summation with sigma notation into a much simpler expression, it's obviously easier to take the limit as n goes to infinity. But the confusion that people get into is that, like I stated in the introduction, telescoping sums, even if the sum is an infinite sum rather than a partial sum, if instead of going to some finite value of n, we were going to infinity, there would still be a finite number of terms due to the cancellation. And so, a lot of people make the mistake in thinking that, okay, there's a finite number of terms, therefore the value obviously converges. Well, that's not true. Just because there's a finite number of terms doesn't mean that the sum of those terms, in fact, converges. Now, in our past example, we in fact do have convergence, right? So if we took the limit of 1 over n plus 1 minus 1, obviously that goes to negative 1, so there is a finite limit as n goes to infinity. However, in the first example, right, we found that our summation was equal to n. So it's clear, obviously, that as the limit as n goes to infinity is infinity. It's not finite. So it's important to understand that just because a telescoping series has a finite number of terms and can be written in a finite way, that does not mean that the sum in total is finite. And I think that's key for people to remember. Alright, so the last thing to note is that if you have an expression, especially with polynomials in it, that you can't do by an arithmetic series or a geometric series, it's worth a look to try to manipulate it algebraically and fit it into this telescoping sum. So, in this case here, if we were to factor that polynomial, we would get an I plus 1 and an I plus 2, right? Well, we notice, right from this point, we can say to ourselves, okay, well, the difference between these two values is 1, right? I plus 2 minus I plus 1 is equal to 1. So it seems like we're headed on the right track. Using, this is equal to, we can use partial fractions. Most of us know it from calculus, right? But again, it's just a little bit more algebraic manipulation, and voila, we have a subtraction of two terms that can easily be written in a form that we know how to use. So, making it simple, we'll say that a sub I is 1 over I plus 1. And so obviously this second term here is going to be 1 over I plus 1 plus 1, or a sub I plus 1, right, which we have right here. So, in other words, this is this, and this is this. And so, using what we know, this sum here is equal to a sub 0 minus a sub n plus 1, as j is less than k. And just by plugging in what we've defined a sub I to be, then it's very, very simple to quickly solve this solution using a telescopic sum. Alright, so I kind of really just put this this information from 1 and 2 here just to summarize for you to be able to see it again at the end. I'm not really going to get into explaining exactly why it works out, because I'm pretty sure I've hammered that home ad nauseum at this point. But I do want to just remind everybody of what this notation here really signifies. And if the absolute value of j minus k in our summation here is 1, that means that that a sub j and a sub k are adjacent terms in a sequence, and that provides for a unbelievable amount of cancellation. That's the typical baseline telescoping sum that we learned in class and that you will see most often, and is not as most useful, but is very useful at illustrating the concept behind a telescoping sum. What I do want to note, though, is that if it's not easy to see, or for example, right, when j minus k was not 1, when it was 2, for example, when I went through that, you can always, and I did this intentionally, and probably, it was a little bit unnecessary, but you can always write out the first couple terms, or write out the first couple terms and the last couple terms, to recognize where the cancellation, the pattern that's occurring in the cancellation. I think that's the most important thing to really try to take away from this module, is that this is pattern seeing. This isn't a geometric or an arithmetic sequence, or summation rather, where we need to manipulate something and force it into an equation or force it into a style. This is more about a more abstract kind of concept of seeing a pattern of cancellation, recognizing it, and then understanding why it's happening. So I would suggest that you go back, if you didn't understand my example that was labeled as advanced, even though it's not really that advanced. The second half of that slide is incredibly important. The part where I talk about fringing and talk about how the parts overlap. Because that's really the key concept in these telescoping sums, is that there are terms that are going to be repeated as positive and negative, and they're going to disappear. So the key is really just to see the pattern of when the what terms are not going to have a corresponding negative term to cancel with them. And finally, I guess I do want to mention that not all telescoping sums converge, and this is right here is a positive, or you have a addition rather than subtraction, so it's not a telescoping sum. And with that, I think that you guys are on your way to understanding the principles behind a telescoping sum, and I hope you guys have a good day.